All right. So let's just refresh our memories first. What does this do? So it's a horizontal one because it sends anything inside the parentheses is a horizontal, right? And we learned that last Thursday. How about this? Close. This is a horizontal translation. Let me write that now.
Oh, that's it.
So I'll write that now. So that's a horizontal translation. Yeah, I'll come back to that one. So if you add or subtract a number, what that does is it's going to I think I'm writing that backwards actually. All right, so if it's a plus, then you're moving your graph to the left. If it's a minus, then you're moving your graph to the right, and that's just a translation. This is a horizontal compression or stretch. It's a compression if the absolute value of A is between 0 and 1, so it's like a fraction number. Actually, I think I'm writing that backwards as well. I'm thinking like verticals. Sorry about that. It's a compression if the absolute value is greater than 1. It's a stretch if it's between 0 and 1. Okay, so we're going to be doing that to trig functions, actually. Okay. Once again, you're not going to write this either. I just want you guys to watch. So we did this earlier, right? We made a table of values for angles and outputs. So at 0, you get 0. At 90, you get 1. At 180, we're back to 0. 270 is -1, and 360 is 0. And there's our graph, right? We did that a little earlier, this unit. So I've got a change here. I'm multiplying theta by 2, okay? So we know that when we plug 0 in here, we get 0. So what would I have to plug in for theta in order to make this whole thing equal 0? So that would still give me 0. So 0, 0 would still give me 0. Now over here I know that when I plug in 90, I get 1. So what would I have to plug in here to get 90 so that I get 1? There you go. What would I have to plug in to get 180 so I still get 0? So it's all going to be exactly how much of the original? Half of it. So half of 360, there's going to be 180. So let's go ahead and take a look at the graph now. So 0, 0 is the same. 45 would be halfway in between here. So 45, 1 is going to be there. 90, 0 is going to be here. 135, -1 would be in the middle of between 90 and 180. And then 180 is back up to 0. And how would you describe what happened to the graph there? It's a compression, right? Just like we would expect. Anytime you multiply by something whose absolute value is greater than 1, it's going to compress your function, okay? Now, we learned a little while back that, what do you call a full cycle of a periodic function? A period. So what does a horizontal compression do to your period? It shortens it, okay? So what is a period? What is a periodic function? We've kind of already talked about that, but it's here again. A periodic function is a function that repeats. And the length of the interval for each repetition is what's known as its period. So horizontal compressions and stretches can actually alter the period of a trig function. Okay, so now we're looking at another one. Same table over here, so I'm just going to rewrite that really quick. That one's staying the same. Let's go ahead and take a look over here. What would I have to plug in for theta so that I get 0, so that I get 0? Okay, what would I have to plug in for theta here so that I get 90, which would give me 1? Okay, so all the numbers are going to be how much now? You add 90 to each one of these, right? And that's because we're subtracting 90 from it afterwards, right? So this is going to be 270, 360, and probably like 450. So now 90 gives me 0, 180 gives me 1, 270 gives me 0, 360 gives me -1, and 450 would be like over here. And so we can tell from comparing the graph on the right to the graph on the left, what did the -90 do to the graph? It's a horizontal translation. It shifted it, right? In trigonometry, that's what we call a phase shift. Okay, you're shifting it horizontally. So they call horizontal translations phase shifts. So there you go. Horizontal translation of a periodic function is a phase shift. Something interesting is consider a sine wave, right, and a cosine wave. We know they look pretty much the same, right? So here's the deal. If I were to take my cosine and continue it back here, and then if I were to cut some of the cosine off over here, that's still a cosine, right? I'm looking at a different place. And if I shift it forward 90 spaces, it'll look exactly like a sine function. So actually, cosine of theta minus 90 is always equal to sine of theta. Okay, it's the same function exactly. That's what we call a trig identity, two equations that look different, but they're actually the same, and we're going to learn a lot about those in Chapter 8. But, all right, so this one gets a little bit difficult because we're combining things here. We're doing more than one thing. We're multiplying and subtracting. What would I put here? Yeah, yes, I will. I'll let you guys think while I get Leilani's page. It's not negative 90, because if I plug in, yeah, 45 works. Let's see why. Because if I plug in 45, 2 times 45 is 90, and 90 minus 90 is 0, and that's what I'm trying to get. So I'm trying to get these numbers over here. So what would have to go here? 90? So let's see, 2 times 90 is 180, minus 90 gives me, which is going to be 1, right? So we're good. Yes, 90. That's interesting. Those ones match. How about the next one? 135? I think you're right. How do you do that now?
How did I do that?
Uh-huh.
I added 45 with 90 because it's a pattern.
Ah, nice job. Okay, that's one way to do it. All right. So what he noticed is that this is a linear function. Linear functions always increase by the same amount. So from here to here is 45. Then you can just go up 45 to find the next one. Okay, that's one way you can do it. Another way that you could do it is you could just take this, right? I keep asking the same question. What would I have to plug in to get what? 270? Let's do 270. What would you just solve that equation, right? You have to add 90 to it and then divide by 2. Okay? So I think, Abel. Sorry. It's never going to stop. So this one's 180. So basically, if you just set this argument is the stuff in the parentheses, if you set the argument equal to the angle you want and solve for theta, you can find it. And you can also do what Abel said, which is use the pattern, because there is a pattern. We're going to do both of those things today. What we're doing is these are horizontal transformations. This would shift your graph to the left or right. This one compresses it. And when you do that, it changes the angles. You remember we've been graphing those trig functions? Remember the angles we've been using? Well, when there's horizontal transformations, they get screwed up. They get messed around. Okay? So we're going to have to start by finding what angles we're going to use first, and then after that, it's actually exactly the same. So that's the goal for today. So horizontal transformations with trig functions. If you have a number in the front here of the theta, that results in a horizontal stretch or compression, and it changes the period. If you have a number here after the minus, that's going to result in a horizontal translation, and it creates a phase shift, is what we call it. Okay. The A is still the vertical, amplitude, and the K is still like the midline. That's still the same. But all right, so let's go ahead and do one here. Go ahead and write down your directions in number 1. Okay. So let me give you guys some steps here. The first thing we're going to need to do is we're going to need to find the angles that we're going to use. We need to find the angles we're going to use. Now, I have some transformations going on here on the inside. I've got a phase shift and a period change there. So all my angles that I usually use are going to get messed up. Okay, so what angles do I usually use for when I'm graphing cosine? Zero. What else? I don't think so. Angles.
So 45.
No. 90. 90. Now I'm leaving a lot of space here, and you'll see why. What I'm going to do is I'm going to set each of these angles equal to the inside. Because I want to find out what would theta have to be to give me that same angle of 0, right? Because that's what the transformation is going to be. So the first thing you would do is minus the 180. Then you would divide both sides by 4. 4 goes into 1845 times, and that's a negative 45. So usually we start at 0, right? But because I've got a phase shift and a period change, now my starting angle is negative 45. Okay? Let's do the next one. That's why I had a lot of space between them, because I need some room to put that 4 theta plus 180. So now I want to figure out how will these transformations change the 90. We found out how it changed the 0. Let's find out how it changes the 90. So I'm going to minus 180 from it. And then I'm going to divide. 45 divided by 2 would be 22.5, I believe. So now the second angle is negative 22.5. It used to be 90, but now it's negative 22.5. Okay? Now, usually, how far apart is 0 and 90 there? Huh? Well, how far apart is 0 and 90? They're 90 spaces apart, right? But now look, how far apart is 45 and 22.5? That's less, right? So that's because of this compression here in the front. It squished it. So now each angle is closer together. Okay? All right, let's do one more, and then after that I'm going to use Abel's trick. Here we go. 4 theta plus 180. So, minus the 180. Divide by 4. Get 0. Okay. So what would you guys say is the pattern here? Because like Abel said earlier, those angles, they're going to go up by the same amount every time. It's going up by 22.5. So if you add 22.5 here, then you get to negative 22.5. If you add another 22.5, you get to 0. So what do you think the next one's going to be?
22.5.
And the next one?
45.
There you go. So you can kind of save yourself some work if you just kind of watch the pattern. Okay? You could go through and just figure them all out. That's an option. So really all you have to do is find the first two, and hopefully if you got the first two right, you could just use that pattern to find the rest. So it's kind of a good idea to maybe do the first three to make sure your pattern's right, but there you go. So what I have now is I had to work for something that was just memorized before. We always started off with 0, 90, 180, 270, 360, but now because of those horizontal transformations, that's a game changer. I've got all different angles now. Okay, so you have to figure them out. Can I erase that? All right, so that's step one, find the angles. I know, it's step one, yeah. Find the angles. All right, so my new angles now are negative 45, negative 22.5, 0, 22.5, and 45. So now the next thing is we're going to graph like usual. Okay, so when we're graphing cosine, we start by putting the angles on there, right? I've got negative 45. I've got negative 22.5, positive 22.5, and 45. And then 0, of course, is in the middle. You want them to be accurately spaced, you know. It doesn't have to be perfect, but it should be reasonable. Certainly wouldn't want to see any negative angles on the right side, right? All right. So after that, we go ahead and graph. So what's our midline?
0.
So the midline, yes, it is 0. The midline, in case you forgot, is the plus k. Now there's no plus k out here, right? So it's going to be right down the middle. And what's the amplitude?
Just 1.
It's 1. So there's no plus k, so that's 0. And then the amplitude is 1. So we're going to go up 1 and down 1. And we just graph like normal. So cosine, where does cosine start? Max, mid, or min? Starts at the max. So I'm going to start way up here at negative 45. That's my new starting angle. And then after that, you just continue the pattern like normal. Now, it doesn't look compressed. It is. But that's because I made the spaces between the angles the same as they usually are. But really, the distance between 45 and 22 is a lot closer than 0 and 90, right? So it's really compressed, but because of the way I drew it, it looks the same as it always does. So really, all the next few days are going to be is just figuring out those numbers. That's it. And reviewing how to graph each one. That's it. What's too much? We will see a few little things, bumps along the way and stuff that come up. But we're going to spend one of our days, our whole day is going to be spent just on radians because, you know, those are kind of ugly. They're fractions and stuff. So. But other than that, it's pretty much the same. So that's that. So let's see how you guys do with it. There you go. I have you tell me what the angles are. So, Nora, what were the angles?
You're doing example 2.
Oh, oops. Thank you. So, Nora, what were our angles for this problem?
40, 85, 130, 175, and 220.
Like that? Okay, cool. And so we go ahead and put those numbers on there. And then we notice that our midline is 0, our amplitude is 1, so once again, it's like the last one. We start now with sine. Where do we? Let me ask somebody for that. Edwards, where do we start for sine? At the midline. There we go. So we start at the midline, and then you go up from there. All right. There you go. Think so?
Well, I just think that should be all we do today.
It's funny. It doesn't seem like that much to me.
Yeah, because you're a math teacher.
No. All right. Write down example 3. Let's do another one. All right, guys. Example. I guess I should have called this example 2, huh?
Yeah.
Maybe did I miss one?
No.
I just misnumbered it. Okay. Oh well.
Not example.
This example 2. All right. So step 1, we got to find our angles. Now tangent has a different set of angles. Okay. Tangent starts with negative 90.
Negative 40.
Yep. Negative 45.
0.
0.
45.
45 and 90. And I'm going to take the argument and set it equal to the angles so I can find my new starting point. And that's it. He's so lazy, dude. All right. All right, we got a fraction here. How do I deal with a fraction? Multiply by that denominator, right? So now my new starting angle for tangent, it used to be negative 90, but now the new starting angle is 0. All right, we're going to repeat for the next angle. Oh, I'm sorry. I can slow down. All right. Ready? All right, continuing. Add 90. Good. Multiply both sides by 2, and I get 90. So what's the pattern? It's going up by? Okay, so I don't need to do the math on the rest of these. I can just add 90. So what's this one going to be? 270, 360. My pattern is plus 90 every time. Okay? Now usually tangent completes a full cycle from negative 90 to positive 90. How far apart are those?
360.
180. But now, how long is it taking to complete a cycle? Now it's 360. This one got stretched horizontally because I have something multiplying the angle that's less than 1, a fraction. Okay? So this graph of tangent is being stretched horizontally and shifted to the right a little bit. Okay? Okay, so let's go ahead and graph it up. So when you're graphing tangent, let's see, we're going to start with our new angles now. It's going to be 0, 90, 180, 270, 360. When you're graphing tangent, what's the next thing you do?
Huh? Oh, graph your midline and maximum stuff.
Not yet. No.
Or
The asymptotes. Yeah. Tangent's the weird one.
Oh, yeah.
So these ones have asymptotes at the beginning and end. Now we're going to plot the midpoint. The midpoint is going to be located at what angle?
The third
Okay, so that's 180. And how high up off the line will it be?
one. One. Or 0.
0. So it's at. So my vertical shift is 0. So it's not going to be up at all or down, or else it's going to be right on the line at the third angle. That's my midpoint. And my amplitude is 1, right? It's not really an amplitude, but we'll call it that. Now, what direction does tangent go? Is tangent an increasing or a decreasing curve? Increasing. So as I go over, I'm going to go up 1 and left down 1. And then concave up. No, that's not right. This side's concave up, concave down. And we're good. And then, of course, you throw a few more on that look just like that.
Do you have to do that?
Yes.
So on the test, they're going to grade us.
I would like you to do at least one to the left and one to the right on all of them. Yes, but you're not in charge. No, actually, these would be very, I can make them multiple choice, but they're very confusing, trust me. Because you know the angles that we find, they don't put them on there. They just give you a graph, and like they always have 90 to 360, and you have to estimate where those lines are hitting. So it's really nasty to try to match your graphics, so I don't do it.
Oh, Mr. Bailey.
Yeah.
Okay, so when we're doing our graphs like this on the test or whatever, like, do they gotta be perfect, like symmetrical? Because mine always look funny.
Well, let me see yours, and I'll tell you if it's okay. It's probably fine. I'm not that picky, honestly, but I'll look just to be sure. If it looks like a cat face, or if it looks like a man waving at me, no, it's no good. But if it's close, we're good. All right, so here's one for you. Now this is cotangent, so I'll warn you. Cotangent has different starting angles than tangent and all the other ones. It has its own little set. So you have to remember what those are to do this one. So go ahead. Amanda, what did you get for your angle for the first one? Eric, what'd you get for your angle on the second one? Cool. Tavier, what did you get for this third one? Correct. Cleopatra, the fourth one? Really? Yeah, that's not one of the angles.
He like writes it down.
That's not one of the angles. Connor's not here. Tammy, what's your fourth angle? Okay. Abel, last one.
Last one, that's 45.
Okay, so there's our new angle. That's the angles we're going to use. So we're going from negative 45, negative 22.5, 0, 22.5, and 45. Najib, what do I do next?
Set your graph.
I did.
Oh, come on. Okay, you put your asymptotes.
I agree. And Cameron, where do I put the midpoint? Right, 0, 0. Sydney, I'm gonna go over and down one.
Yeah.
And the reason it's going to be down is because it's cotangent. And then don't forget to put your other ones on there. And we're good to go. All right, so that'll close us out.